Friends, hello friends, good morning wherever you are, and I welcome you to this episode of Learning Physics with me. You're welcome to Learning Physics with IBM. For those who are on this channel for the first time, you may consider to subscribe, share the information with friends so that they can also use this resource for learning physics. Remember, this is Physics 970. This is Physics 9701. Physics 9702, not 9701. Physics 9702, that is Cambridge, paper 4. And we are still on our unit of thermal properties, and we said it would be divided into three parts. We saw the ideal gases, where we saw the equation of state, pressure of a gas, kinetic energy, the kinetic theory, and so on and so forth. We have already seen thermodynamics and internal energy, where we were able to see the first law of thermodynamics. And at this point, you should be able to use the concepts of the first law of thermodynamics. We shall see many of them in details when we look at the past paper questions. Later on, that will be at the end of this unit. So today, I want us to continue to the last part of thermal properties, that is now temperature. I told you the order doesn't matter. Some people would prefer to start with the temperature before they look at ideal gases and thermodynamics. I prefer to start with ideal gases. The order to me doesn't matter. So we are going to look at temperature, and to be specific, I want us to look at thermal equilibrium and temperature scales. Of course, for now, that is for now. Of course, temperature, this unit will be a little bit longer than the previous two. This part of thermal properties will be a little bit longer than the previous two because we shall see thermal equilibrium. This is brief. Temperature scales is also brief, but we have also to see the thermal properties of materials, the atomic spacing. We shall also talk about specific heat capacity, thermal capacity, and so on and so forth. So for now, let's start looking at thermal equilibrium. I think our everyday idea of temperature is based on our sense of touch. Many times, for example, when you touch, let me draw a simple physics student here. So let us assume there are two dishes. Let this be dish A, and let's have another dish B, and let's have one particular physics student, perhaps a lady, and this lady touches in the two dishes at the same time. So dish A has crushed pieces of ice, and dish B is placed on a heating flame, on a burning flame. Water, let's say there is water here which is on a burning flame. So this particular person will get a sensation that this side is cold. Perhaps if it is ice, it is 0 degrees Celsius. I don't know whether somebody can touch in boiling water, but let's say this is heat. That means the water is at a relatively higher temperature. So um, normally our normally our everyday idea of temperature is based on a sense of touch. We cannot really smell and say, okay, the temperature is high. So by putting your hand into a cup of ice or a container containing ice, immediately you get a sense of cold. And when you put the hand or the other hand into water which is put on a burning flame, immediately you get a sense of hot. Therefore, we conclude that we can get that sense or the difference in the two senses because this is at a lower temperature and the other water is at a higher temperature. So in other words, the water on the flame is at a higher temperature than ice. Now think about a situation where one end of a metallic object, maybe an iron bar, is placed on a burning flame. Let's assume that maybe the other end is placed in a cup which is containing crushed pieces of ice. So we place a burning flame somewhere at this end. This could be maybe, I don't know whether a candle can work. So let us assume that this is an iron bar. One end of the iron bar is placed on a gun or just above a burning flame. So this is at a higher temperature. Let us assume that this is at 70 degrees Celsius. Burning this side is initial at 70 degrees Celsius. And because this side has crushed pieces of ice, then it is at 0 degrees Celsius. So there is a difference in temperature on this end A and the other end B. So what shall we observe after a small period of time? Of course, after a small period of time, we shall see that actually the crushed pieces of ice start melting. And after a long period of time, we shall see that all the ice has melted. But there was no heat applied this side. The heat was only applied on the other side. Why did the ice start melting? Assuming that the container was initially perfectly insulated, that we can assume no heat is gained or absorbed from the surrounding, still we shall see that our ice is going to start melting. The reason is very simple. There is an effect of difference in temperature between the two ends of the object. And that effect is that thermal energy is going to be transferred, or heat energy is going to be transferred from end A, which is at a higher temperature, to end B, which is at a lower temperature. So, there is a net flow of heat from a region of high temperature to a region of low temperature. I think that is natural. Naturally, heat flows from a region of high temperature to a region of low temperature. So let us assume that after a certain period of time, maybe we remove the flame and we also remove maybe the ice. We have already asked, the ice has already helped us to tell or to identify that actually there is a net flow of thermal energy from end A to end B. So naturally, heat flows from a region of high temperature to a region of low temperature. In fact, if the burning flame is placed this side where there is ice, still, if all the ice melts and the temperature this side rises above the other end, still we would notice that heat starts flowing from this end to the other end if the temperature this side rises above the temperature on the other end. So, whenever we have two different bodies or two regions at different temperatures, then there will be always thermal energy flow from a region of high temperature to a region of low temperature. This flow of heat continues until a point when thermal equilibrium is attained. So you might be asking yourself, what is therefore meant by thermal equilibrium? So, in the first place, let us assume that we now removed the ice and we have removed the flame. With the time, we shall realize, since the flame is not there and the ice is also no longer there, with the time we shall realize that the temperature of end A will become the same or equal to the temperature of end B. Then the question would be, in which direction will heat therefore be flowing? Heat or thermal energy naturally flows from a region of high temperature to a region of low temperature. Then suppose now end A and end B have now reached the same temperature. So here we say that thermal equilibrium has been established. When two ends or two regions or two bodies in contact are at the same temperature, we say that thermal equilibrium has been established. But of course, the mode of transfer of heat using in solids is very easy. You saw this in IGCSE. Let's think of atoms inside a solid. Remember, atoms have a property called rigidity. They do not move from one point to another point, but their motion is restricted to vibration about the equilibrium position. So think of one atom which is close to the flame. This atom gains more energy because it is very close to the heating source, Therefore, it vibrates more violently, passing on its energy to the neighboring atom, which also starts vibrating more violently, passing on its energy to the neighboring atom, which also vibrates more violently. So with the time, it means all the atoms now will be vibrating. When when the 2 points bring about a change in temperature are removed, all of a sudden, after a certain period of time, we shall see that the temperature at end A is the same as the temperature at end B. We are saying at this point, we say that thermal equilibrium has been established. We say that thermal equilibrium has been established. When the whole ion bar reaches the same temperature, when all parts of the ion bar reach the same temperature, then we say thermal equilibrium has been set up. Therefore, whenever different regions or bodies in thermal contact are at the same temperature, they are said to be in thermal equilibrium. Whenever two different regions or bodies or points or parts in contact are at the same temperature, they are said to be in thermal equilibrium. During the process of reaching thermal equilibrium, I want you to note that there will be no net thermal energy flow, no net flow of energy in any particular direction, because the heat only flows from a region of high temperature to a region of low temperature. But suppose two ends of the material are at the same temperature. Does it mean there is completely no heat? I am using the word flow. There will be no net flow of thermal energy in any particular direction. In fact, the flow of thermal energy all over the material is equal in all directions. That's why I'm saying there is no net flow of thermal energy in any particular direction. Okay, so I must have put this in a simple summary that whenever different regions or bodies in thermal contact are at the same temperature, then we can say that they are said to be in thermal equilibrium. The same temperature is very important. Two regions, 2 points are the same temperature. They are said to be in thermal equilibrium, and when thermal equilibrium is established, then there is no net thermal energy flow in any particular direction. There is still energy, there is still flow of energy, but there is no resultant flow of energy in any particular direction. We therefore say thermal equilibrium has been established. Okay, so I want people to note that it is going to be wrong for you to think that there is no transfer of thermal energy between 2 points or bodies, even when the temperature is constant. So you would be right to say that there is no net thermal energy flow or transfer, unlike when the 2 points or two bodies are at different temperatures. So when I say thermal equilibrium has been established, I do not mean that there is no flow of thermal energy. Flow of thermal energy is still there. There is flow of energy in different directions equally, but there is no net resultant flow of energy in any particular direction. In fact, I want you to understand the concept of thermal equilibrium as if it is some kind of dynamic situation where the transfer of heat between two objects or regions is actively going on in all directions at the same rate. There is heat transfer in all directions at the same rate. So we can simply say that there is no net flow of thermal energy in any particular direction, as long as the temperature between the 2 points is the same. So I have mentioned the temperature. So I want people to know or to recall that temperature should be understood as a scale of hotness. And since heat flows from a region of high temperature to a region of low temperature, it means the word temperature is indicating a certain scale which helps us to indicate the direction of net flow of thermal energy. Heat itself is a form of energy which can be transferred from region of high temperature to region of low temperature. Therefore, heat is a form of energy which only flows due to a difference in temperature. So there is a simple link and a simple contrast between the term heat and temperature. Heat being a form of energy which only flows as a result of difference in temperature. Yet we earlier on saw that temperature was dependent on the kinetic energy of the molecules. Therefore, recall always that temperature is the average kinetic energy of the molecules that make up the system. So, temperature here is going to tell us the difference or the degree of hotness or coldness of a body with respect to some standard. Actually, relying on temperature, you cannot tell the heat energy or the amount of heat energy. However, you can only predict the direction in which heat will flow if there is a difference in temperature. So we think about temperature as the average kinetic energy of the molecules which make up the system. So it means earlier on, as we had seen, that if the total kinetic energy of the molecules has increased, it means the average kinetic energy has also increased. Therefore, the temperature should be increasing. But the more precise way of defining temperature would always be in terms of the average kinetic energy rather than how we defined it as the degree of hotness or coldness of a body with respect to some standard. Of course, geographically, temperature is the degree of hotness or coldness. But if I ask for room temperature, somebody will say 20 degrees Celsius. So what does this mean? It's like a temperature is a number. It's actually a number which expresses the degree of hotness or coldness of an object, of a place, to mention but a few. Okay, so that is all I could say about thermal equilibrium. At this point, you should be able to define thermal equilibrium. At this point, you should be able to define thermal equilibrium. Next, let's talk about the temperature scales. We said temperature should be understood as a scale of hotness, which is going to help us to indicate the direction of flow of energy. And we have seen that the degree of hotness or coldness of a body or an object is measured with respect to some standard. Therefore, there is need for what we call temperature scales. I don't think this is the first time you are hearing of temperature scales. I know you have been talking about temperature scales, particularly you have talked about the Kelvin scale and the degree Celsius scale or the so-called centigrade scale. So various degrees of hotness are represented by a temperature scale. What is very important at this point is how to establish a temperature scale. How do we establish a temperature scale? And of course, to come up with a temperature scale, we need a thermometric scale. So how do we come up with a temperature scale? Before we come up with a temperature scale or uh, a thermometric scale, we need two important things. And these are, we need to come up with a thermometric property. Thermometric property. You can't come up with a temperature scale without choosing what we call a thermometric property. A thermometric property is actually a physical property which varies or it changes linearly with the temperature. We always assume that this property will change linearly as temperature changes. In fact, is going to be directly proportional to or inversely proportional to temperature, but following a perfectly linear relationship. Although sometimes we shall see that we just assume it varies linearly, but it may not perfectly vary linearly. So a physical property which is assumed to vary or change linearly with the temperature is what we call a thermometric property. We shall see some thermometric properties used in everyday life. Number two, you may need, a thermometric property is a physical property which is assumed to vary or change linearly with the temperature. That is a thermometric property. Rather than a thermometric property, you also need to come up with what we call fixed points. In fact, we need two fixed points. You cannot establish a thermometric scale or a temperature scale without fixed points. These fixed points should be 2 degrees of hotness or degrees of coldness, which can easily and accurately be reproduced every time, 2 degrees of hotness which are easily and accurately reproducible are going to be the ones we call fixed points. For those who studied IGCSE, you at least have an idea about fixed points. For example, you have the upper fixed point if it is water, for example, the upper fixed point and the lower fixed point. We shall also talk about another one which you may not have heard of, which is called the triple point of water. These ones are degrees of hotness which can easily and accurately be reproduced several times. So we rely on these ones together with a thermometric property or a physical property which is assumed to vary linearly with the temperature to come up with what we call a temperature scale or a thermometric scale. What are some of the examples of these thermometric properties which vary linearly or are assumed to vary linearly with the temperature? Examples of thermometric properties which vary or we assume to vary linearly with temperature. Number one, we have the volume of a liquid or the length of a liquid column. Most liquids or many liquids expand when the temperature increases. For example, you have seen a mercury in a glass thermometer. When you place it in boiling water, you see the mercury inside raising because the volume is increasing or the length is increasing as the temperature increases. So the property here is the volume of the liquid or the length of the liquid column. Alcohol also expands when the temperatures increase. So alcohol can also be used to come up with a temperature scale or to come up with a thermometer, as to be specific. So volume of a liquid changes with the temperature. So we can consider it to be a thermometric property. Number two, we can talk about the resistance of a wire or a thermistor. We have seen that for a thermistor, for example, its resistance decreases when the temperature increases. We call it a negative coefficient thermistor in electricity. But the other ordinary wires, their resistance also increases when the temperature increases. We have already seen that. But for a thermistor, its resistance decreases when the temperature increases. So resistance of a wire or resistance of a thermistor is a thermometric property or a physical property which is varying with temperature. Although for a thermistor, we are much aware that it does not vary linearly. The resistance does not vary linearly with the temperature, but we can still use it as a thermometric property because it changes with the temperature. Number three, we can talk about the EMF of a thermocouple. The EMF of a thermocouple can also be considered to be a thermometric property. For those of us who studied IGCSE, you remember for a thermocouple you needed a sensitive meter where you needed two wires of different materials joined together to form two junctions. So somewhere here you could have a microvoltmeter. One junction is kept at a certain temperature. Let's say this junction is kept in ice, that is say at 0 degrees Celsius. And the other junction can be placed in a liquid in any substance whose temperature is required. Note that this could be copper, that wire could be copper, and this could be another material, maybe nickel. So the two wires should be of different, made out of different materials. So Whenever there is a difference in temperature here, it will be correspond to a difference in the EMF generated. So that is actually a thermocouple. So this is what we call thermoelectric EMF. There is when the difference in temperature between the two junctions changes, the corresponding voltage read here is going to be changing, or the EMF generated here is going to be changing. Therefore, we say that the EMF of a thermocouple can also be used as a thermometric property. Number 4, the pressure of a fixed mass of a gas at constant volume. We have already seen earlier on that a gas exerts pressure on its container. So it means if the volume remains constant, if the temperature increases, the pressure of course also increases. So the pressure of a fixed mass of a gas at constant volume can also be thought of as a thermometric property. Of course, if the volume is not constant, pressure may increase and the volume also increase, so the temperature may not actually change much. So if the volume is constant, there will be a significant change in temperature or in pressure as the temperature increases or decreases. There will be a significant change. And maybe the last one is the color of an electrically heated wire. In which unit is that? Was it astrophysics and cosmology? We saw Wien's displacement law, that the color of or the radiations emitted, the intensity of the radiations emitted is maximum at certain wavelengths. In fact, at shorter wavelengths. So when you continue heating a material, you see its color changing. If a wire is heated, you will see its color changing. So those colors could give us a clue about the temperature. For example, we said our sun appears yellow because its surface temperature is approximately 6,000 Kelvin. So we know that when a material glows yellow, its temperature should be close to 6,000 Kelvin. So the color of an electrically heated wire could be used as a thermometric property. Then on the other hand, how about the fixed points? Let's talk about the fixed points. Fixed points, the examples of fixed points, remember I said these are 2 degrees of hotness which can be accurately and easily reproduced. They can be reproduced several times accurately without any problem. Number 1, the most common ones are these two. That is the ice point, which we mentioned in IGCSE. The temperature of pure melting ice is what you call the ice point, and it is assigned 0 degrees Celsius. The temperature of pure melting ice. By the way, ice with impurities may melt at a temperature slightly less than 0 degrees Celsius. The temperature of pure melting ice is what we call the ice point. I know some people will think about the ice point as that point where where ice melts. But the temperature the temperature of pure melting ice is 0 degrees Celsius. Normally, when ice is not melting, it is at a temperature far less than 0 degrees Celsius. It could even be as low as negative 10 degrees Celsius. Number 2, we have the steam point. These two are the most commonly used fixed points on thermometers or on temperature scales. The steam point is known to be the temperature of steam coming from pure boiling water. The temperature of steam coming from pure boiling water. By the way, if water is not pure, if water has impurities, it may not boil at the known temperature. So this is assigned a value of 100 degrees Celsius. But of course, this is also depending on other factors. Rather than impurities, it could also be depending on the height above sea level. So the temperature of steam coming from pure boiling water is what we call the steam point. So how do we then come up with a temperature scale? That could be now the question you could be asking yourself. How do we come up with a temperature scale? We have now our thermometric property. we have now our two fixed points. So how shall we come up with a temperature scale? So somebody might be wondering, I said we have two temperature scales, which we shall talk about. Of course, there could be others. We shall only talk about the centigrade scale or the degrees Celsius scale and the thermodynamic scale, the so-called absolute scale or the Kelvin scale. Of course, some people would talk about degrees Fahrenheit and so on and so forth, but we shall only talk about those commonly. So how would we come up with a thermometric scale or a temperature scale? When I talk about a scale, when you look at a thermometer, you will see marks. On an ordinary thermometer you find in the laboratory, you will see marks ranging from negative 10 degrees Celsius to around 110 maybe. For some of those designed to measure body temperature, they could be they could not go that far. But those used in the laboratory could be going up to 110 degrees Celsius. So you might be wondering how they come up with those marks, how they come up with that calibration on the thermometer. That's what we are now referring to as establishing a temperature scale. So we have the thermometric properties. We choose a thermometric property. Which property do you want your thermometer to use? Like the ones we use in the laboratory are going to be relying on the property which is the volume of a liquid or the length of a liquid column. Because the length of the liquid column rises, for example, if it is using mercury or alcohol in the laboratory, the length of the liquid inside will rise or will fall to indicate a change in temperature. So it means we have now chosen our property to be maybe the length of a liquid column or the volume of a liquid. If I have finished to choose a property, then I have to look at the two fixed points. So I look at the property at 0 degrees Celsius. So I will measure or I will take the thermometric property at the two fixed points. Taking the thermometric property at the two fixed points and I divide the range between the two fixed properties, between the two fixed points into equal steps. Then I'll be establishing what we are going to call the empirical scale of temperature. So what am I trying to say? You have a thermometric property which you have chosen. Let me call that property X. So I have chosen my property X. It is the volume of a liquid or the length of a liquid column. So I will measure X at 0 degrees Celsius. In other words, using a ruler, I'll measure the height of the liquid in the mercury glass thermometer when the thermometer has been placed in ice or melting ice. That means I have measured the property at the lower fixed point. Then I measure the property, I'll call it X100 at the steam point. I'm using the two fixed points, which is the steam point and the ice point. So I measure the property at the steam point. In other words, I'll place the thermometer in pure or in steam coming from pure boiling water. So I want to come up with the divisions or the marks on the thermometer, or I want to calibrate the thermometer. So what do I do next? Then I will get, let's say I measured, I noted that the height here was say 10 when placed in pure melting ice, and let's say the height here was 70 when placed in steam coming from pure boiling water. So I have a range between 70 and 10. This range between 70 and 10 is going to be divided into equal steps. When I divide these into equal steps, we establish, or I will be establishing, what we call an empirical scale. Empirical. Chemistry students talk about empirical many times. They talk about the empirical formula, but they forget that it is a formula which has been derived by experiment. So we can set up what we call an empirical scale of temperature for a thermometer. The word empirical here is meaning derived by experiment. Empirical is meaning derived by experiment. Empirical is meaning derived by experiment. So we have measured the property at ice point, that is the lower fixed point. We have measured the property at 100 degrees Celsius or at steam point, and now we are dividing the range between between the value for the property at ice point and the value for the property at steam point. Remember, ice point is correspond to 0 degrees Celsius and steam point is corresponding to 100 degrees Celsius. So we divide that range into equal steps. So if we choose to divide the range, into 100 equal divisions or 100 equal degrees between the temperatures correspond to the two fixed points, taking 0 or to the two fixed points taken as 0 degrees Celsius and 100 degrees Celsius, then we have arrived at what we call an empirical centigrade scale. So when we divide the range between the two values, or the range between the points where we have measured the property at ice point and measure the property at the steam point, we come up with what we call an empirical centigrade scale of temperature for that particular thermometer. Now I want you to note that there is nothing special about these two fixed points, the ice point and the steam point. The only thing is that these 2 points can be reproduced several times, but there's nothing special about them. In fact, if you're very observant, you realize that these 2 points actually may not really be very much fixed, because they also depend, or they can change if the pressure changes or if the material is not pure. If water is impure, the steam point is not 100 degrees Celsius. If the pressure if the pressure changes, the boiling point or the steam point and the ice point may not still be the same. So there is nothing special about them. So remember, we have assumed that the property X varies linearly with the temperature, because we say the thermometric property is going to be assumed to vary linearly with temperature. So I can sketch a graph. Of the property against temperature. Remember, I have measured the property at 0 degrees Celsius and the property I've called it X naught. I have measured the property at 100 degrees Celsius and I've called the property X100. So it means I can now, because I'm assuming that the property varies linearly, therefore it means I can just use these 2 points to draw a straight line. And if I draw a straight line, I can always use that straight line to measure or to determine any other temperature. So I have established what I have called a centigrade scale. But then, from the reason as to why I've drawn this graph is to help me simplify, or to help you to come up with a simple formula, which I will always discourage students to cram. First of all, you just assume the property varies linearly with the temperature. If you have the property at a lower fixed point and the property at a higher fixed point, the 2 points should give you a straight line. So from that graph, you can always come up with a simple value for another property. So we have now measured the property at a certain temperature which is not known. And the value of the property is x theta, but we don't know theta. We may want to find theta on the centigrade scale. This is a straight line, so the gradient must be constant. Therefore, I can take, I'm finding the gradient, so I can say x 100, x 100 minus x naught, that is the change in the y, is going to be 100 minus 0. That is the change in the y. This gradient should be the same if I take another pair of points. So this will be x theta minus x naught. This is x theta minus x naught divided by theta minus 0. So the gradient is the same because it's a straight line. I want theta. I'm trying to make theta the subject. So x 100 minus x naught divided by 100 is going to be equal to x theta minus x naught divided by theta. So when I make theta the subject by cross multiplying, so theta is going to be x theta minus x naught divided by x 100 minus x naught. Of course, this will be times 100. Now this is on a centigrade scale, so it means I would be measuring theta in degrees Celsius, so this will be the answer in degrees Celsius. So this expression here, some students normally prefer to cram it, but it is easy. You just look at the property varying linearly with the temperature. From the property, you come up with a straight line. So that is what we call the centigrade scale. Now, I wanted people to realize that it is actually very important for us to realize that uh, the choice of the thermometric substance we use in a thermometer, that is either alcohol or mercury, for example, and the property we have chosen, that is, if we choose a volume of a fixed mass of a gas, pressure, or a volume of a liquid, these will determine the centigrade scale we obtain. In fact, the choice of a different thermometric substance and a thermometric property may lead to a different centigrade scale, may give a different Celsius scale. There will be agreements between the scales at fixed points. The question will be, why does this happen? Or what does it actually mean? You may get two thermometers, one using, say, alcohol, another one using mercury, in the same room, and the two thermometers may give a slightly different room temperature. That's what I'm trying to talk about. This implies that the two thermometers are giving two different centigrade scales. So in other words, I'm trying to say that there could be a variation, there could be a discrepancy, there could be a difference in two centigrade scales, even if they are taking the same measurement, or they are being used for the same experiment. So they could slightly be different. Then the question would be, why does this happen? Why is it that two thermometers used at the same point may not actually agree on the measurement being taken? I said it is important to realize that the choice of a different thermometric substance and a thermometric property may actually sometimes lead to a different centigrade scale. However, these two thermometers will always agree, or are most likely going to agree, only at the fixed points. There be a systematic error or a random error? Not at all. There may not be a systematic error or a random error. But remember, we have assumed that the thermometric property varies linearly with the temperature. We have just assumed. It is not always the case. Because we just assume that the thermometric property varies linearly with the temperature, yet it is not always the case, then there would always be a variation in the values of temperature measured. Therefore, the thermometric property may not always, or may not perfectly vary linearly with the temperature as it is always assumed. The thermometric property may not vary perfectly linearly with the temperature as it is always assumed. But experiments by scientists have indicated that the difference or the discrepancy in the measurements between two thermometers becomes smaller and smaller if we use thermometers which are relying on gases as thermometric substances. When we use thermometers relying on liquids, there could be a large difference in the centigrade scales. But experiments have shown that if we use thermometers relying on gases, there is a very small difference in the centigrade scales. So it is very important to note, it is very, very important to note that the choice of a thermometric substance is very important. It is also very important to note that although we assume that the thermometric property varies linearly with the temperature, many times or sometimes it does not perfectly vary linearly with the temperature. What is the implication of this? The implication will be that two centigrade scales may never agree, even when they are measuring, taking the same measurement. This is because the thermometric properties may not vary perfectly linearly with the temperature as they are always assumed to be or assumed to. So I also mentioned that it has been found or established by experiments that for thermometers which use gases, two different thermometers but using gases may still disagree on a measurement, but the difference between the measurements is relatively small. So it even becomes smaller if the gases are actually at a certain higher pressures, because we shall later on see that there exists a point when the gas now behaves as ideal. And if a gas starts behaving as ideal, then it obeys the equation PV is equal to N RT. And if it obeys the equation PV is equal to nRT, you will notice that the pressure is directly proportional to the volume. And this is a perfectly linear relationship. The volume is directly proportional to temperature, which is a perfect linear relationship. So we are saying, before we leave this, that one, we can establish a centigrade scale. We measure the property at the two fixed points. And of course, we divide the range between the two fixed points into equal steps to come up with what we call a centigrade scale. If we divide this into 100 equal steps, it is a perfectly an empirical centigrade scale. From that, since we know that, or we assume that the property varies linearly with the temperature, the values at the two fixed points could give us a straight line. From the straight line, I was able to establish that the temperature in degrees Celsius can be given by the property at the unknown temperature minus the value of the property at 0 degrees Celsius or ice point, divided by the temperature at steam point minus the temperature at ice point, then multiplied by 100. Our answer will be in degrees Celsius. But we have said two thermometers or two temperature scales may not disagree, especially if they are on a centigrade scale. The reason as to why they may not agree is because we always assume that the thermometric properties vary linearly, but they may not actually vary linearly as we have always assumed. However, I mentioned that the difference between the empirical scales are smaller in the case of thermometers which use gases as thermometric substances. Whether the property is pressure of a gas, as long as the thermometers are using gases, the difference in the measurements taken using two different thermometers relying on the gas is not very large as compared to other thermometers relying on other substances such as liquids. So let us try to explore the volume. Maybe before we go to the volume gas thermometer, let's do a few examples so that people can learn how to come up with this expression. Example number one. Example number one. The value of resistance in a piece of wire is 3 ohms at the ice point. That means ice point, remember, I will call this the property at ice point. This is the properties, of course, resistance. So at ice point, I will say resistance at ice point, I'll call it R naught is 3 ohms. and it is 80 ohms at steam point. So the properties R at 100, that is R at steam point, is actually 8 ohms. What is the temperature of the wire if its resistance is 5 ohms? So we want the resistance at the unknown temperature is 5 ohms. So we want to tell the unknown temperature. So if we assume that the resistance varies linearly with the temperature, then since this is just a wire, it's not a thermistor where it decreases, you see that the resistance is actually increasing, because at ice point it is 3 ohms, at steam point it is 8 ohms. So this will be a straight line. I will simply sketch a straight line for clarity. It is easier to understand when I sketch a straight line rather than cramming a formula. So resistance against temperature, this will be a straight line. Remember, I have measured at 0 degrees Celsius. The property is 3 ohms. And then at 100 degrees Celsius, the property is giving me 8 ohms. So it doesn't require to be genius to see that 5 ohms is somewhere in between 8 and 3. So let's say 5 ohms is somewhere there, and I want the temperature corresponding to 5 ohms. I'll call this one theta. Because this is a straight line, I may assume that the gradient is constant, so I will find the gradient. Using 2 points, I'll have 8 minus 3 divided by, this was 100 minus 0, that is the gradient. I can use another set of points. This will be 5 minus 3 divided by, this is going to be 3, this is going to be theta minus 0. 8 minus 3, that is 2, no, that is 6, divided by 100 is going to be equal to 5 minus 3, which is 2, divided by theta. Cross multiply, that means the theta is going to be 2 over 6 times 100. 2 over 6 divided by 100, that is 200 divided by 6. That means our temperature theta is going to be 33.3 degrees Celsius. So the temperature corresponding to 5 ohms is approximately 33.3 degrees Celsius. Without even cramming the formula, I could just think of oh, by the way, this is 5, not 6. Sorry, this is 8 minus 3, which is 5. Okay, so this is going to be 5, not 6. So this is just a small error, slight slip of the mind. So 200 by 5, this gives you 40 degrees Celsius. Okay, so that is 40 degrees Celsius, the temperature corresponding to 5 ohms. Okay, example number 2, we shan't waste any much time on that. Example number 2, the length of the mercury column in a mercury glass thermometer is 25 millimeters. So the thermometric property here can still be identified. It is a mercury in glass. The property is volume of a liquid or length of a liquid column, because for a mercury in glass, we look at the mercury rising inside when you place it on anything to measure the temperature. So that is length of a liquid column. So I'll use L for length. The length of the mercury column in mercury glass is 25 millimeters at the ice point. So I'll say L naught is 25 millimeters. That is at ice point. It is 180 millimeters at steam point. L 100 is 180 millimeters. What is the temperature when the length is 55? So L theta is 55 millimeters, and theta is not known. So one, we just assume that the length of a liquid column varies linearly with the temperature. and you see there is an increase. So if length varies linearly with the temperature, that gives us a straight line graph. Length with the temperature, that will give us a straight line graph. And we just sketch 2 points. If theta is 0, the other one is 25 millimeters. So let's say that is the point. And if theta is 100 degrees Celsius, let's say the other one is 180 millimeters. So let's say this is the point plotted. These 2 points, because L varies linear with the temperature, should give you what? A straight line. And if they give you a straight line, then you can be able to estimate when L is 55, that is between 25 and 180. So let's say 55 millimeters is still somewhere here. So this is going to help us to find theta. So we have these 2 points, this point, we have this point here, we have this point here. So we don't need to cram any formula, we just look at the gradient, think about the gradient. So the gradient 180 minus 25, that is change in y, change in x is 100 minus 0. This should be the same as when I subtract 55 minus 25 over theta minus 0. Let's subtract 180 minus 25, that is 155 divided by 1, this is 100, should be equal to 55 minus 25, which is 30, divided by theta. Making theta the subject by cross multiplying, that becomes 3000 divided by 155, and this is giving me 19.4 degrees Celsius. So that will be the temperature, or the unknown temperature, if the length is 55 millimeters. By the way, what we are doing normally is sometimes called calibration. This is sometimes called calibrating a thermometer. To calibrate a thermometer is to make it possible to use that thermometer even when it has no marks on it. If I can tell, if I know the temperature of, or if I know a property at 0 degrees Celsius, and I know a property at 100 degrees Celsius, then I can estimate the temperature, of course, by simply calculating. That is going to be what we call calibration. So this will be 19.4 degrees Celsius. 19.4 degrees Celsius. Okay, maybe one more example. Maybe one more example. Let's call it example number 3. Example number 3. A resistance thermometer has a resistance of 95.2 ohms. That is at ice point. So we have that resistance, the properties resistance of the thermometer. So resistance at ice point is actually 95.2 ohms and 138.6 ohms at the steam point. So we shall say resistance at steam point R at 100 is 138.6 ohms. What resistance would be obtained at a temperature of 19.4 ohms? What resistance will be obtained at a temperature of 19.4, no, not ohms, at a temperature of 19.4 degrees. So we want resistance at 19.4 degrees, and this is not known. Resistance at 19.4 degrees. Let's assume that we are seeing that at ice point, the resistance is 95.2 ohms. Then at steam point, the resistance is higher. That means resistance, first of all, is directly proportional to temperature. If I sketch a graph for guidance rather than cramming a formula, so at 0 degrees Celsius, let's say the resistance is 95.2 in ohms. This is resistance against temperature. So we have a point here for 0 degrees Celsius and 0 degrees Celsius. Then at 100 degrees Celsius, that is at steam point, let's say the resistance has been given as 138.6 ohms. So let's say the point is somewhere here when I plot. So because we have assumed that resistance varies linearly with the temperature and we are seeing an increase, so we shall have a straight line. We shall have a straight line. Then we want the resistance at a temperature of 19.4 degrees. So temperature of 19.4 degrees Celsius is somewhere here. So I will have to find the resistance. The resistance is most likely going to be in between these two. This is the resistance that I want. That is the resistance at that temperature. Let me call it R theta. So I'll just use the gradient because I've assumed that the temperature varies perfectly linear with the resistance, or resistance varies perfectly linear with the temperature. Remember, this is not always the case. We just make an assumption. So taking the gradients, I have that 138.6 minus R theta is going divided by 100 minus 19.4. This should be equal to R theta minus 95.2 divided by 19.4 minus 0. So I got no, there's a challenge here. This is 100 minus, this is 100 minus 19 point, not, we have 138.6 minus R theta over, yeah, this is 100 minus 19.5. I think that is correct. Then the other one is going to 0, yes. So we are making R theta the subject. Let's just cross multiply this. It is quite long, but we shall bear with it. So this will be 19.4 multiplied by 138.6 minus R theta. This should be equal to, the other one is 100 minus 19.4. The other one will be 80.6 into R theta minus 95.2. So we are opening the brackets. I'll open the brackets at once, for you can go ahead and do all the steps you want. Me, I will have 80.6. I subtract 19.4. So I have 61.2. That is R theta should be equal to. The other side I have, so this side I have 19.4 times 138.6. When I bring this side to be plus, open brackets, 80.6 times 95.2. So this side I have 1036 1.95. I think I need to check R theta. When I bring this R theta this side, I think it will be plus, not minus. So this is minus, this is plus. So this is not true. So I have 80.6 plus 19.4, which is giving me 100. So that is 100 R theta. So it means the R theta is going to be 100 divided by, 10361.95 divided by 100, which becomes 103.6 ohms. So the resistance at 19.4 degrees Celsius is going to be 103.6 ohms. I think that is a very good example. That could be a very, very good example. Very good example given. Okay, let's proceed. Let us proceed. I think we said the difference in the thermometers could easily, becomes smaller if we use a constant volume gas thermometer. I think from this at that point, you should first of all have to do this self-check, a quick self-check to verify that you can always look at the thermometric property and its relationship with the temperature and find the missing property or the missing temperature. Make sure you attempt this self-check. The EMF of a certain thermocouple is 5.6 millivolts when one junction is placed in melting ice and the other in steam. With one junction in melting ice and the other in a boiling liquid, the EMF is 2.46. Capture the boiling point of the liquid on the centigrade scale of this thermocouple. Number 2, the gain of an electric circuit is found to depend on temperature. At 5 degrees Celsius, the gain is 110, and at 18 degrees Celsius, it is 125. Assuming that the gain depends linearly on Celsius temperature, estimate the gain when the circuit is used on a hot day at a temperature of 25 degrees Celsius. Number 3, the resistance of a thermistor is 3500 ohms at 2 degrees Celsius. At 20 degrees Celsius, its resistance is 1800. You notice that here it is a decrease. Here it is a decrease. That means your graph cannot be a straight line going upwards. The thermistor is used as a thermometer. What will be the recorded temperature when the thermistor is the thermistor resistance is 2150 ohms? If the resistance of the thermistor is assumed to vary linearly with the temperature, suggest why the temperature measured using a mercury in glass thermometer may give a different value for the temperature. Then explain why two thermometers using a centigrade scale may give different values of room temperature when used at the same time. So you can attempt that self-check before you proceed to the next part. In our next part, we want now to explore the constant volume gas thermometer. Earlier on, we have just mentioned that on the centigrade scale, two different thermometers or two different temperature scales relying on the centigrade may not agree. However, we say the disagreement becomes smaller when we use thermometers relying on gas or using gases as thermometric substances. A thermometric substance is a substance which is used in a thermometer. For example, we have mercury is used in a mercury in a glass thermometer. You have alcohol and so on and so forth. That is a thermometric substance. And I am saying for those thermometers which use gases as thermometric substances, the difference in their measurements is very, very, very small. The question will be, what is unique about this constant volume gas thermometer? So here I have my thermometer by the way. Note that this thermometer is not, it's not actually, it is an experimental thermometer. It's just practical. You know, you can't use this to measure your body temperature, of course. You can't use the constant volume gas thermometer to measure your body temperature. But you can still use it, but it is quite about, it comes as a setup. So here we have a gas, here we have a liquid in here. Because it is a constant volume gas thermometer, the property here is going to be the pressure. So the thermometric property is going to be pressure. So we are going to see that if two thermometers relying on gas, even if the gases are different, even if the thermometric properties are different, the difference in temperature measured by the two thermometers will become smaller or becomes smaller. In fact, the difference in the temperatures or the difference in the scales of the different gas thermometers becomes even lesser and smaller if the pressures used in this experiment are smaller, or if the pressure of the gas is even smaller. Why? If the gas continues to remain as a gas, at a very small pressure, then this gas may not be assumed to be a real gas. In fact, the pressure will vary more linearly with the temperature, or even the volume will vary more linearly with the temperature at lower pressure. If the gas still exists as a gas at lower pressure, then the pressure will vary more linearly with the temperature. The volume will vary more linearly with the temperature. Decreasing the pressure of a gas, which is a real gas of course, will make it behave as if it is an ideal gas. And if it starts behaving as if it is an ideal gas, then we recall that for an ideal gas, PV is equal to nRT, or simply PV over T is equal to a constant. At low pressure, a real gas behaves more like an ideal gas. And for an ideal gas, PV over T is equal to a constant. So, if we decide to set up an empirical centigrade scale for a real gas at a in a constant volume thermometer, by obtaining the pressure of the gas at, for example, we put our gas in in ice. We put the gas in melting ice, pure melting ice. So we measure the pressure. We measure the pressure of the gas at ice point. That will be my pressure of the gas. I've measured the pressure of the gas at steam point. That is at 0. Of course, by the way, even at 0 degrees Celsius, the pressure of the gas cannot be 0. Then we can still measure the pressure of the gas at steam point, that is at 100 degrees Celsius. So I have measured the pressure of the gas at steam point. So the pressure of the gas at steam point, this is the pressure of the gas at steam point, and I'm calling it P100. So this is at 100 degrees Celsius. Of course, because we know that at low pressure, the variation in pressure with the temperature is perfectly linear. This will automatically give me a straight line, as you can see. But then, if I try to look for the pressure at which, no, not the pressure. If I try to find the temperature at which the pressure of the gas ever becomes 0, because at 0 degrees Celsius, the pressure of the gas is found not to be 0. If I try to find the temperature at which the pressure of the gas would become 0, I want to use the word would because practically we may not reach there. If I try to find the temperature at which the pressure of the gas would become 0, I will extrapolate this line further downwards. I extrapolate the line. I don't know whether this is, I think it's extrapolating. I extrapolate the line backwards. The extrapolated line experiments have found this value at which the pressure, at which the value of the temperature at which the pressure becomes 0 for a gas to be very close to negative 273 degrees Celsius. So, experiments by several scientists using a constant volume gas thermometer has realized or have always found out that when the graph is extrapolated backwards, it falls onto or very close to negative 273 degrees Celsius. If the experiment is repeated at even lower pressures with the gases at lower and lower pressures, the experiment shows that the extrapolated value tends to approximate negative 273.15 degrees Celsius. By the way, this value here, negative 273 degrees Celsius, or negative 273 degrees Celsius, negative 273.15 degrees Celsius is what we call the absolute zero, on what we are later on going to define as the thermodynamic scale. Negative 273 degrees Celsius or negative -273.15 degrees Celsius is what we call the absolute zero on another scale which we call the thermodynamic scale. Scientists believe we can't go beyond -273 degrees Celsius. No experiment can, or they believe no temperature can be reached below -273 degrees Celsius in practice. Remember I said for lower temperatures for lower pressures of the gas, the exact value is approximately -273.15 degrees Celsius. So many times we shall always either use 273, -273 or -273.15. And I am saying this temperature here, -273.15 degrees Celsius is the same as 0 Kelvin. So it is considered to be absolute zero on another scale which we are going to define as a thermodynamic scale. It is called the absolute zero simply because it is called absolute zero simply because it does not depend on particular substances. It does not depend on any particular substance. It does not depend on any thermometric property. It does not depend on any particular substance. In fact, you can see we reached -273 by just extrapolating our graph. So perhaps we can say -273 is simply an extrapolated value. But of course, before we go any further into the sweetness and the beauty of the absolute scale, let's try to come up with a formula here. If pressure varies perfectly linear with the temperature, then if it is a straight line, I'm going to find the gradient still. So taking the gradient, you will notice that pressure P100 minus, which one should I use? Okay, I can use P at 0, that is P100. Okay, let me just use P naught, P100 minus P naught, divide by P naught minus 0. Now let me just use direct gradients. I will use direct gradients because this will confuse some of us. P100 minus P naught divided by 100 minus 0 should be equal to, this should be equal to, this will be P naught minus, this will be P naught minus, this will be P naught minus, P naught minus 0 divided by, the change in temperature will be 0 minus -273. Okay, I think that is true. I think that is. Okay, so this would be one way of relating these. This could be one way of relating these temperatures on the Celsius scale. But I'm not interested in relating them on the Celsius scale anymore because that would be not very important for now. So let's understand the absolute scale in details in our next slide. For now, let's stop the constant volume gas thermometer here, but at least we have seen that from the constant volume gas thermometer, we are able to estimate the smallest temperature that is expected to be reached. Of course, in practice, we shall see that this value has never been reached, but scientists come, or experiments come a few millionths of degrees close to -273 degrees Celsius. I mentioned that we call it absolute zero on the thermodynamic scale. It is called absolute zero because it does not depend on any thermometric property or any thermometric substance. Let's see it in details, the absolute scale of temperature. Let's see the absolute scale of temperature in details. First of all, we have seen the previous explanation that the extrapolated temperature is found to be -273 on the centigrade scale. And we have seen that when experiments are repeated with lower and lower pressures, the value actually becomes, or the value is actually close to -273.15. And I mentioned this temperature is known as the absolute zero on the thermodynamic scale. And I said it is called absolute zero because it does not depend on the thermometric properties of any particular substance. It does not depend on thermometric properties of any particular substance. You have just seen the previous slide that we just extrapolated to arrive at the absolute zero. Let's fully understand the next temperature scale. All along we have been talking about the centigrade scale. I think now we qualify to talk about the absolute scale. Sometimes it is called the Kelvin scale, but precisely it is the centigrade scale. How is this different from the one we have already seen? So the absolute scale of temperature, one, we have already seen that it does not depend on any property of any particular substance. It does not depend on the thermometric property of any particular substance. Of course, sometimes it's called, or commonly it is called the Kelvin scale, but I prefer to call it the thermodynamic scale. So what makes this unique? What makes it a different scale? By the way, the thermodynamic scale is a better scale than the centigrade scale, simply because one of its fixed points, which we are going to see, or which we have already seen, by the way, one of its fixed points is called the absolute zero. Remember I said to come up with a temperature scale, we must have a thermometric property and fixed points. But we are saying the absolute temperature scale does not depend on the property of any particular substance, because one of its fixed points, the absolute zero, has a very great significance than any of the two fixed points that we had seen on the centigrade scale. So this property, this scale, the Kelvin scale, is far different from other scales, simply because when we are setting it up, we do not rely on any particular property of any particular substance. Note very carefully that one of its points is very significant, and we call it the absolute zero. It is more significant than the fixed points of the centigrade scale, which are actually variable, or they can change when there are impurities. When the pressure changes, the ice point or the steam point could change. But for the absolute zero, does not depend on any of those particular substances. And scientists sometimes suggest that at absolute zero, there is completely no energy left in a material or in a substance. And I think that is really not true. It's not correct. Of course, we believe that at absolute zero, from what we saw in ideal gases, that at temperature equals to zero, the average kinetic energy of the molecules or atoms which make up the substance can be considered to be zero. But how about the potential energy contribution to internal energy? All we can say is that at absolute zero, it is impossible to remove any more energy from a material or from a substance. When a substance is at absolute zero, the kinetic energy of the molecules is actually zero. But the electrical potential energy may not be zero. It could be minimum, that no more energy can be removed from a substance. So we say that at absolute zero, the temperature at which all substances have minimum internal energy could be the absolute zero. Minimum internal energy. In fact, the only contribution is the potential energy of the molecules. By the way, I want to always emphasize that absolute zero in practice has never been reached. But experiments have come within just a few millionths of a degree close to the absolute zero. So when we talk about the absolute zero of temperature, I want people to know that it is different from other scales, simply because we did not set it up depending on any property of a particular substance. Number two, it, it is a better scale simply because one of its fixed points, the absolute zero, has greater significance than either points of the centigrade scale, which are actually variable depending on the environment, or impurities vary the centigrade fixed points. Number three, I've also mentioned that it's not possible to have a temperature lower than 0 Kelvin. We believe it is the smallest we can reach. We cannot have a temperature less than negative 273.15 degrees Celsius, which is called the absolute zero on the Kelvin scale. Number four, although sometimes people suggest that at 0 Kelvin matter has no energy, I say that is strictly not true. All we can say is that for any matter at absolute zero, we can't remove any more energy from it. I mentioned that internal energy is going to be minimum because kinetic energy is zero, but potential energy is very, very small. So we are saying here, absolute temperature is the temperature at which all substances have minimum internal energy. All substances have minimum internal energy. The kinetic energy of the molecules will be zero, as we have already seen in ideal gases, but the potential energy contribution is going to be minimum. And I want people to note that this has never been reached, even though we come within a few millionths of a degree. We haven't reached 0 Kelvin in practice, but of course, it doesn't mean that it's a useless scale. At least we come close within a millionth of degrees. So there are a few points that we need to note about the absolute scale of temperature. One, I want us to note the fixed points first. Maybe let's first talk about the fixed points so that we shall go back to the constant volume gas thermometer and come up with the expression for temperature on the thermodynamic scale. So we said we need two fixed points to establish any temperature scale. We saw for the centigrade scale, we had the lower fixed point, which is the ice point, and the upper fixed point, which was the steam point. Now, how about for the thermodynamic scale? Already we have established one fixed point, which is the 0 Kelvin, which is the absolute zero, which we say that it is not possible for a temperature to be less than the 0 Kelvin. So the other fixed point, of course, we have seen that the 0 Kelvin is on the constant volume gas thermometer, which was in degrees Celsius. We saw it is negative 273.15. But of course, many times we just use negative 273 depending on the conditions, as we are going to see. There is another fixed point other than the absolute zero, and this is called the triple point of water. Triple point of water. These are the two fixed points on the thermodynamic scale. The triple point of water is that temperature at which ice, that is solid, water, that is liquid, water vapor, that is gas. In other words, the three states coexist at the same time in equilibrium. So there is a temperature assumed for the three states of matter to exist at the same time. That temperature, if we have water, that temperature is called the triple point of water. Water exists as ice, it exists as liquid, it exists as vapor at the same time. That is called the triple point of water. Of course, it is hard for anybody to think about the triple point of water, but international agreements have defined this temperature to be 273.16 Kelvin. That is approximately 0.01 degrees Celsius. International agreements have shown or have agreed that water can exist as a liquid, gas, and vapor at around 0.01 degrees Celsius. So we take the triple point of water to be the upper fixed point on the thermodynamic scale, as the absolute zero is the lower fixed point. Now I want you to be very careful. You should not confuse 273.15 with 273.16. This is Kelvin. This, when I put a negative here, this is in degrees Celsius, this is the same as absolute zero. But this one here is 0.01 degrees Celsius. This is actually called the triple point of water. So the absolute zero of an ideal gas, for example, on the constant volume gas thermometer, we saw it was negative 273.15 degrees. But then we are seeing that the triple point of water is given by 273.16 according to international agreements. That means if the international agreements give us 273.16 Kelvin as the triple point of water, if I change it to degrees Celsius, it is 0.01 degrees Celsius. We shall see how to convert this later on. Now, our scientists have chosen, or Kelvin to be specific, chose the gap between the triple point of water, 0 Kelvin, that is between 0 Kelvin and 273.16 carefully Kelvin, that the gap between these two values are equivalent or are equal to the gap between the divisions of the centigrade scale. The gap between the absolute zero and the triple point is divided into 273.16 equal divisions. So it means each division on the Kelvin scale is actually 1 Kelvin, each division. Remember, we saw that the gap on the centigrade scale was divided into 100 equal divisions, meaning that if the property at ice point, that is 0 degrees Celsius, and at steam point, that is 100 degrees Celsius, when we divide the gap between 0 degrees Celsius and 100 degrees Celsius into 100 equal divisions, it means each division is 1 degree Celsius. So, if we think of a constant volume gas thermometer like we had done before, where we had a pressure against, it was pressure against temperature. At low pressures, at low values of pressure, we saw that at 0 degrees Celsius, the pressure was a certain value, it wasn't zero. Then at 100 degrees Celsius, the pressure was a certain value. Let's say this is pressure at 100, and let's say this is pressure at 0 degrees Celsius. Then we sketch a graph. This was a straight line. Sorry. So this was a straight line. This was a straight line. We try to, of course, extrapolate this downwards until it touched negative 273 point, I want to be specific, and I say 0.15 degrees Celsius. Now remember, we are now calling this one 0 Kelvin. We are calling this one, let me use a different ink because I don't want to change the page. We are calling negative 273.15, we have called it 0 Kelvin. And we have said the other fixed point is the triple point, which is above 0. It is around somewhere here. This is 0.01 degrees Celsius, which is on the Kelvin scale. This will be 273.16, which is the triple point of water. So if we can measure the pressure at the triple point, if we can measure the pressure at the triple point, I will call that PT. So this is 273.16 Kelvin. So we have these 2 points. They are very, very important, the triple point and the Kelvin scale. So if we consider this, then we can still find the temperature at a given, or the pressure at any different temperature. So let's say we want now the pressure when the temperature is, say, theta, or we shall use T for the Kelvin scale. So we want this pressure here, we'll call it P. So because it's a straight line, I'll take the gradient. So at this point, the pressure is P. So I'll say P at the triple point minus, this is 0. The pressure here is 0, divided by the triple point of water, which is 273.16, minus the temperature here is 0 Kelvin. I'm using the 0 Kelvin, should be equal to the unknown pressure P minus, again is 0 because the pressure here is 0, divided by at P, the temperature is T on the Kelvin scale minus the absolute 0, which is 0. So if I want to find T, you will notice that T, therefore, will be equal to, I'm making T the subject, T will be equal to the pressure over the triple point of water PT, over the pressure at the triple point times 273.16. So on the Kelvin scale, remember this will be in Kelvin units, so this will be in Kelvin. So I've just manipulated this. If pressure at this point is P at temperature T, this is a straight line. I tried again to take a gradients. Pressure at the triple point minus pressure at the 0 point, at the 0 Kelvin, that is 0, divided by temperature at the triple point, which is 273.16 in Kelvin, minus temperature at the absolute 0, which is 0, is equal to the pressure at the unknown temperature, which I called P, minus pressure at 0 divided by temperature minus the original temperature, which is 0 Kelvin. So this gives us the temperature on the Kelvin scale to be equivalent to that value. Let's try to see if we can use this to attempt a few examples. So here we are saying that the triple point, let me first clear this, erase this. Let me first erase this. So we are saying that the triple point is found to be less dependent on environmental conditions, such as pressure, as compared to the ice point. Then I also mentioned that a gap between the absolute 0, which is 0 Kelvin, and the triple point of water, which is 273.16 Kelvin, is divided into exact 273.16 divisions, so that each division is going to be 1 Kelvin. We shall see what is the importance of this. Why should each division be 1 Kelvin? Why should we divide the gap between 0 Kelvin and 273.16 Kelvin into exact 273.16 divisions? Now somebody may be wondering, how can we divide something into 273.16 divisions? The 0.16 could be bothering many of us. Okay, let's first do a few examples, 1 or 2. I think 1 will be enough for this because it's not something very common. The pressure reading of a constant volume gas thermometer is given as 1.5 at triple point of water. So pressure at triple point is 1.50 times 10 power 4. Remember the triple point is 273 Kelvin. This is in pascals. When the bulb is placed in a certain liquid, the pressure is, so the pressure, the unknown temperature is 4.28 times 10 power 3 pascals. I will simply call it A. Find the temperature. So we have seen that the temperature, the unknown temperature is the pressure divided by pressure at triple point times the triple point, 273.16. So this will be equal to pressure, which is 4.28 times 10 power 3 divided by the triple point, which is 1.50 times 10, pressure at the triple point, 1.5 times 10 power 4, then times 273.16. Okay, where is my calculator? So we press the calculator here. So when I press my calculator, this is giving me a 277.9 Kelvin. So if you're a chemistry student, such a liquid is most likely going to be, I think that is nitrogen. That is most likely going to be nitrogen at its boiling point, 77.9 Kelvin. Okay, number two, I think number two can be yours. Self-check number two, we already have self-check number one. The pressure reading of a constant volume gas thermometer is given as that at steam point. Remember, steam point is 100 degrees Celsius. What is the pressure reading at the triple point of water? The pressure reading at steam point is given as 100, is given as that. What is the pressure reading at the triple point of water? So that one is your assignment. That will be your assignment. There are a few points we need to note. Number one, there are a few points we need to note as we wind up this lesson. Which points do we note? Number one, I told you first of all, there is a reason as to why the scale, the gap between 0 Kelvin, absolute zero, and the triple point, that is 273.16, is divided into 273.16 equal divisions. Why is that important? So this is the importance. So the scale on the centigrade on the Kelvin scale, or the scale on the thermodynamic approach, is defined in a way such that scalar divisions on the thermodynamic scale are equal in size to divisions on the centigrade scale. Of course, the importance of this is that converting is going to be something very easy. If one division on a centigrade scale is equal in size to one division on the Kelvin scale, then converting from degrees Celsius to Kelvin, or from Kelvin to degrees Celsius, it becomes very, very easy. So this means that a change in temperature of 1 Kelvin is going to be the same as a change in temperature of 1 degree Celsius. A change in temperature of 1 Kelvin is going to be the same as a change in temperature of 1 degree Celsius. So these are defined in such a way to make 1 Kelvin exactly the same size as 1 degree on the Celsius scale in size of division. This could be something not very, very common to most people. What does that mean? A change in temperature of 1 Kelvin is equal to change in temperature of 1 degree Celsius. What does that mean? Let me give a simple example, though it is not the right time to give this example. Let's say the temperature T1 of a room is actually 0.5, not a room. The room cannot be at 0.5 unless it is in those countries which experience winter. So let's say T1 is 10 degrees Celsius and T2 is 20 degrees Celsius. What this statement is saying that if there is a difference in temperature on the Kelvin scale, it will be the same as the difference in temperature on the Celsius scale in magnitude. If I find this difference on the Celsius scale, this will be 20 degrees Celsius minus 10 degrees Celsius, which will give us 10 degrees Celsius. This is the change. But I want you to note, if I want this change on the Kelvin scale, it will be wrong mathematically to add here 273. I know some people know how to convert already. So that means I will need T1 on the Kelvin scale will be 10 plus 273. T2 on the Kelvin scale will be 20 plus 273. Then the change in temperature on the Kelvin scale will therefore be 20 plus 273 minus 10 plus 273. And this will give you exact 10 Kelvin. So that's what I mean by a change in temperature on the Kelvin scale being equal to a change in temperature on the centigrade scale because of the size of the scale divisions on both scales. The units of temperature, remember, on the Kelvin scale are just degree and are not degrees Kelvin. They are simply Kelvin in the memory of this person called Kelvin. So the units should never be written as degrees Kelvin. And remember also that on this scale, the highest point, which is 0, is 273.15 Kelvin. By the way, it is only given as 273.15 Kelvin if it is 0.00 degrees Celsius. If it is 0 degrees Celsius, then it is given as 273 Kelvin. Precision is very important. The steam point, which we know as 100 degrees Celsius, is going to be 373 Kelvin. If the precision is 100.00, then it is going to be noted as or denoted as 273.15 Kelvin. So precision is very important. I'm emphasizing precision here. When temperatures are given to one decimal place, for example, if we have 20.4 degrees Celsius and I want to quote this in Kelvin, so I can't add 273 here. I will instead add 20.4, add 273.15 instead of 273. And when I press my calculator, this is 20.4 plus 273.15. This gives me 293.55, but because this was given to one decimal place, the corrective value for this would be 293.6 Kelvin. If this had been given as 20.04, then I would quote two decimal places in Kelvin using this. Those who have ears must have listened, and those who have eyes must have seen. When the temperature is quoted as a whole number, when you are converting, remember to just use 273. When the temperature is quoted as a decimal number, then you quote 273.15. But remember to round off on the exact number of decimal places as the value of temperature given. I hope I've made myself clear on that. So lastly, you are going to always ensure that all calculations are done in Kelvin units rather than degrees Celsius. All the calculations we shall interact with will always be in Kelvin units rather than in degrees Celsius. At this point, I expect that people should now be able to convert. So to convert, we already know that to convert from degrees Celsius, if I want to convert from degrees Celsius to Kelvin, of course, I'll use T for Kelvin, capital T for temperature in Kelvin, theta for temperature in degrees Celsius. So if you were to convert from degrees Celsius to Kelvin units, then it is very easy. For example, convert 10.1 degrees Celsius to Kelvin. Here you just add 10.1 plus 273.15. You simplify this. Remember, it is quoted to one decimal place, 10.1 plus 273.15. This is giving me 283.25, but because this is quoted to one decimal place, this is going to be 283.3 Kelvin. So from degrees Celsius to Kelvin, we add. From Kelvin, temperature in Kelvin, changing it to degrees Celsius, here we subtract. For example, convert 300 Kelvin to degrees Celsius. This will be 300 minus 273. So that will be 300 minus 273. This gives you 27 degrees Celsius. Remember the precision. Remember the significant figures. Self-check number 3. Self-check number 3. You will have to convert all these. Remember the rules on decimal places. Remember the rules on decimal places. to maintain the precision. So convert. The values we are using, choose 273 if the value quoted is a whole number. But remember we said for lower values of pressure of a gas, the value is very close to 73.15. So choose 273.15 as long as the value of temperature given is not a whole number. So does it therefore mean that we have the best scale of temperature, the best temperature scale? Maybe yes, maybe no. We may not have the best temperature scale, but it is actually the best for now. What could be the challenge with this temperature scale? When do we use it in everyday life? Somebody could be asking such questions. So all this will be summarized in my conclusion. In my conclusion, there is a problem. There is a problem with this scale. The problem with the centigrade scale is that the thermometric properties do not always follow a straight line relationship between the two fixed points. So all along we just assumed that the thermometric properties vary linearly. That was a big problem with the centigrade scale. So it meant that the centigrade scale was very inaccurate at all points except at the fixed points. Two different centigrade scales could agree at the fixed points and disagree at all other temperatures. Number two, does it mean we have now a better scale using the absolute? If we wish to compare temperature accuracy between two different experiments, you can't rely on the centigrade scale because the variation is not perfectly linear. The absolute scale would be the most perfect scale since it has an absolutely straight line relationship between temperature and the property, of course, as long as the gas used is at low pressure. Does it therefore mean this is very, very useful? Unfortunately, the problem with this scale is that it is theoretical. This is a theoretical scale. The problem is that the absolute scale we have all along been talking about, although it would be the best scale for use, it would be the perfect scale because uh, it has an absolute straight line relationship between temperature and the property. Unfortunately, this is a theoretical scale. This scale is theoretical. First of all, in practice, we don't have an ideal gas. So it means this scale is actually ideal. Although some constant volume gas thermometers can get close to its perfect behavior, but this does not mean that it is even any less useful. There is nowhere you'll find this scale being used. So we are saying that the absolute scale is simply a theoretical scale. So this marks the end of temperature lesson 1. There will be several lessons. I will call this one lesson 1. So this marks the end of temperature lesson 1. However, at this point, I'm giving several, I've so far given 3 self-checks. I'm adding another self-check. Self-check number 4. Explain why the centigrade scale is said to be empirical. That is self-check number 4, question number 1. Question number 2, explain why two thermometers tend to give different values of temperature even when used for the same experiment at the same time. I think that question is repeated. You may not repeat it. Explain why the absolute scale is said to be absolute. That is, there are 2 questions in this self-check. Self-check number 4, there are 2 questions. Number 1, explain why the centigrade scale is said to be empirical. Number 2, explain why the absolute scale is said to be absolute. Self-check number 5 is a reading assignment. Self-check number 5 is a reading assignment. And here is the reading assignment. You are going to read about practical thermometers because this is IGCSE. There are rarely questions about practical thermometers in A-level. This is IGCSE. Once in a while you find a question of 1 mark anyway. So you are going to read about practical thermometers that you studied in thermophysics in IGCSE. Especially I'm interested in the thermocouple, majorly the thermocouple, and the constant volume gas thermometer is not, we have already explored it, most especially the thermocouple. When reading about these practical thermometers, emphasis should be given to the range of temperatures that they can measure and their sensitivity. The range of temperatures that they can measure is very important. In IGCSE, you talked about characteristics of these thermometers. You talked about the range, which was actually the difference between the highest and lowest temperatures that can be measured by this thermometer. You talked about sensitivity, linearity, but for now, since we started this in IGCSE, I want us just to concentrate on the range of these thermometers. And therefore, if you know the range of the thermometers, you should be able to identify which thermometer can be used where and why. What are the advantages of using it? So you should read about practical thermometers. You should be able to read about practical thermometers. And that will be the end of lesson 1, temperature lesson 1. See you in temperature lesson 2. See you in temperature lesson 2. Have a good day. Bye bye. Oh, by the way, I had forgotten, this should be submitted together with all the self-check exercises. You should submit this with all the self-check exercises that are in this document, in this video. All the self-check exercises, I think there are 4, and this is the 5th. So make sure you submit all the self-check exercises. I now prefer more work to be uploaded on Teams. If you can attach your work in the one notebook, in the class notebook, it will be very fine. It will becomes easier for me to mark. When you send it when you send it as a document, it means I just have to get a piece of paper and outline what you have failed before I assign you the marks. But if you were to attach it in the one notebook, I can even put their ticks. Otherwise, have a beautiful day. Bye.